Hello everyone. Today we are going to extend the static version of the new classical model to including realistic labor market frictions. It is still a static model because the decisions in one period only affect the current period. And it is still a micro-founded model because all behavioral equations are strictly derived from microeconomic principles. The difference is to introduce search and matching frictions into the model so that the model is more realistic. In the last lecture, we have seen that the static version of the new classical model can explain the majority of the business cycles by productivity on the supply side. However, it cannot explain the business cycle stylized facts in the labor market well, because all employment is voluntary in the competitive market. To explain involuntary unemployment, especially during the Great Depression, Keynesian models introduce nominal friction or nominal rigidity in wage and prices, which lead to a disequilibrium analysis. If we want to explain unemployment within the new classical convention without introducing nominal rigidity, an alternative approach is to assume search and matching friction in the labor market. We know that it takes both time and money to search for the right person and match with the right job in reality. This is ignored in the previous new classical model, where labor demand and labor supply are matched instantly. The reason for search and matching is asymmetric information. Firms do not know the right job seekers, so there are always vacancies and unemployment at the same time. To elaborate on what we mentioned in the previous slide, the new classic static model can only explain the acyclicality of the intensive margin, but cannot explain the procyclicality of the extensive margin. If the labor market is competitive and information is symmetric, then there should not be any involuntary unemployment. However, in the data, we see that vacancies and unemployment coexist all the time. There is actually a negative relationship between vacancy and unemployment in the data, which is termed as the Beveridge Curve. To explain more stylized facts as such, we must introduce more realistic assumptions. Today, we will introduce the Diamond-Mortensen-Passarides or DMP model, which takes into account the search and matching friction in the labor market to be able to explain the extensive margin and the Beveridge curve observed in the data. The first learning objective today is to familiarize yourself with different measures of business cycles in the labor market. Then, we will further distinguish measures in the intensive margin and extensive margin. Next, we will compare the new classical model and the DMP model. Finally, we will apply the DMP model to explain the extensive margin in the labor market. Here is a big picture to show you where we are. We are still in the static model chapter, which is the static version of the new classical RBC model. The DMP model extends the RBC model by introducing search and matching friction. Now let's take a look at some more stylized facts in the labor market, which form the new research questions to be answered by our new model. As summarized in lecture 0.3, there are some stylized facts of business cycles in the labor market, as shown in table 3.2. I repeat this table above to remind you. Apart from these, we will introduce some more measures and stylized facts specific to the labor market. On the supply side of the labor market, let's denote N as the working age population and Q as the total labor force, which is defined as the employed workers, M, and the unemployed job seekers, U. On the demand side of the labor market, A is the total number of jobs available, which is defined as the sum of the filled positions, M, and the unfilled vacancies, V. In measuring the extensive margins, we usually use the following metrics. Note that the denominators of unemployment rate and employment rate are different. Specifically, we will use the labor market tightness, J, which is defined as the ratio between vacancies and labor force. It implies vacancies per worker, or how easy one can find a job. A higher J means an easier job market. I use the diagram to the right to illustrate the relationship among all these measures. You can pause the video now to familiarize yourselves with all these different measures. In the data, we can see counter-cyclical co-movements between unemployment rate and GDP on the left, and pro-cyclical co-movements between participation rate and GDP on the right. Furthermore, vacancy rate and unemployment rate tend to move in opposite directions, which we term as the Beveridge Curve at the bottom. These new stylized facts in the labor market are our new research questions to be answered by our new model, the DMP model. Now let's specify the 4 building blocks of the DMP model. As you can see, the supply side and the demand side of the DMP model are basically the same as the static model we have discussed in the new classical model. There are 2 additional building blocks in the DMP model. One is the search and matching mechanism. The other is Nash bargaining. The 2 additional assumptions must hold at the same time because if the market is no longer competitive, there is always a bargaining process going on. This diagram shows you how the model is constructed. Like the new classical model, we also have representative consumers and firms. But the difference is that we add search and matching mechanism and Nash bargaining mechanism in the labor market now. The first building block is the labor supply, or consumers. Each of the N consumers can choose to work outside the labor market or looking for jobs inside the labor market. As illustrated by the diagram, Q denotes those who look for jobs inside the labor market. So N minus Q are those who stay outside the labor market. When you stay outside the labor market, you may simply enjoy leisure and do nothing. Or you may do home production like housewives and house husbands. They are non-participants of the labor market, but it doesn't necessarily mean they are not contributing. On the supply side of the labor market, the number of job seekers, Q, should increase as the expected payoff of job seeking rises. This can be derived from a micro-founded optimization problem of consumers. There are 2 possible outcomes of searching for work. On the one hand, if she or he finds a job, she or he will be employed and receives the wage W. The probability of this case is the number of workers who find jobs, M, divided by the number of job seekers, Q. On the other hand, if she or he fails to find a job due to asymmetric information, she or he will be unemployed and receives an unemployment insurance, B. The probability of this case is equal to the number of workers who cannot find a job, Q minus M, divided by the number of job seekers, Q. Therefore, the expected payoff is equal to the probability weighted average of the 2 cases. Remember that the number of job seekers, Q, is an increasing function of the expected payoff on the left-hand side. To make it general, we use an increasing function of Q, PQ, on the right-hand side to indicate this positive relationship. For example, the increasing function PQ can be a positively sloped linear function 2 plus 3Q because it increases with Q. In the tutorial, you will have an explicit function form of PQ to allow you to solve the solution, but here let's keep it general by keeping the implicit function form PQ. The second building block of the DMP model is the demand side, or firms. To repeat the definitions of the notations, A is the total number of vacancies available, while M are filled vacancies. We also assume a fixed cost of posting a vacancy on the internet or newspaper. Firms that do not post a vacancy are inactive and no costs are incurred. Like consumers, firms will choose the optimal number of vacancies, A, such that the expected payoff is maximized. Unlike consumers, due to competition, if the expected payoff is positive, there will be more firms entering the market, so the expected payoff must be driven to zero. There are also two possible outcomes of opening a vacancy. On the one hand, if the vacancy is filled, the profit is equal to the output of the worker Z minus the wage cost W and minus the fixed cost of posting the vacancy K. The probability of this case is equal to the number of matched vacancy M divided by the total number of vacancies A. On the other hand, if the vacancy is not filled, the profit is equal to minus K, only the cost of posting the vacancy. The probability of this case is equal to A minus M divided by A. The expected payoff is a probability-weighted average, and it must equal to zero due to competition. The third building block of the DMP model is new. Since there is asymmetric information in the market, search and matching is not frictionlessly done. The number of being matched is a function of three variables, E, Q, and A. E is the matching efficiency, just like Z in the production function. It measures the overall efficiency of matching the supply and demand sides of the labor market. It depends on technological progress like the internet and the big data technology. Q and A are grouped together by an implicit function M. It is assumed to have constant returns to scale, or CRS, which means when you double Q and A at the same time, you will double the output of M of the two variables. It resembles the production function of labor and capital in producing output of the firm's problem. The intuition of this assumption is that when more people are searching for jobs and more vacancies are available, it becomes easier to get matched. Here are two important properties of the matching function to be highlighted here. We will use the two properties later in analyzing the model. The first property is that if the function MQA is divided by A, it is equivalent to a decreasing function of job tightness J, M1 over J, 1. In other words, the function of Q and A can be transformed to a function of J. To see this, let's specify the function M as a Cobb-Douglas specification, which is a constant returns to scale function. So MQA is equal to Q to the power of mu multiplied by A to the power of 1 minus mu. Remember that the function is a general form of input and output. So if we replace the first input Q by Q over A and replace the second input A by 1, we have M Q over A and 1, which is equal to Q over A to the power of mu and 1 to the power of 1 minus mu, which is basically Q over A to the power of mu. To prove that M QA over A is equal to M 1 over J and 1, we start with the left-hand side of the equation. We divide M, Q and A by A. Use the law of power functions. When the bases are the same, the powers can be combined. So we can rewrite M of Q and A over A as Q over A to the power of mu, which coincides with the results of M of Q over A and 1 as we shown earlier. The definition of J is A over Q, So we prove that m of q and a over a is equal to m of 1 over j and 1. Similarly, if we divide the matching function by q, then it can be written as an increasing function of j. I will leave this as a practice for you to prove this second equation. The fourth and the last building block of the DMP model is Nash bargaining. It is inevitable to have this accompanying assumption along with the search and matching assumption, because if there is no such friction, there won't be any bargaining issues. You either take the job or leave the job. The firm can always find someone to fill the vacancy effortlessly, and the consumer can always find a good job effortlessly. But once search and matching is costly, the choice of leave it becomes costly too. It takes substantial effort to find an alternative, so bargaining becomes necessary. It is just like marriage. The reason that the couple stick together may not be that they love each other so much, but because breaking up is too costly. That is why bargaining or arguing always happen between couples. We know that the total surplus for consumers is equal to the benefit of finding a job, which is equal to wage W, minus the opportunity cost of finding a job, which is the social insurance benefit B. The total surplus for firms is equal to the benefit of filling a vacancy, which is equal to the marginal product of labor Z, minus the cost of hiring the labor, which is equal to the wage W. The sum of the consumers and firms' surplus is equal to W minus B plus Z minus W, or just Z minus B. The Nash bargaining is about how to split this total surplus, Z minus B, between consumers and firms. In modern societies, the shares of the firm and the workers depend on the political bargaining powers of the two sides. In the UK, it is basically represented by the Conservative Party and the Labour Party. In the US, it is represented by the Democrats and the Republicans. Let's denote the bargaining power of the workers or unions by A, and that of the firms or capitalists by 1 minus A. Therefore, the consumer's surplus W minus B must be equal to the share A multiplied by the total surplus Z minus B. Similarly, the firm's surplus Z minus W must be equal to the share 1 minus A multiplied by the total surplus Z minus B. Both conditions can be rewritten as the equilibrium wage W equal to A multiplied by Z plus 1 minus A multiplied by B. It is a weighted average of Z and B. To clarify, political bargaining powers A is exogenous. So are Z and B. W is exogenous to individual consumer and firm, but endogenous to the labor market when you combine the supply and demand sides. To summarize, we collect the 4 building blocks of the model. The first 2 are optimal behavior of the consumer and the firm. They describe the relationship between expected payoff and the decision of Q and A. The third equation describes the aggregate matching equation to explain how M is determined. The final equation describes how wage W is determined after combining supply and demand. It is straightforward to substitute equation 3 and 4 into 1 and 2 so that we can maintain a supply side and demand side in the model. To do this, we substitute out M and W, and we need to use the 2 properties of the matching function we have derived earlier on slide 13. I leave the derivation to you for practice. The supply and demand sides after substitution are shown here. The green terms are exogenous variables, which you can use to explain the red terms, the endogenous variables. Note that, like before, the lecture uses implicit function forms to keep our conclusions general, so you cannot solve explicit solutions of the endogenous variables like Q and J. But in the tutorial, I will give you a specific function form for the matching function M, so that you can solve all the endogenous variables by exogenous variables. The two condensed functions can be drawn in graphs to illustrate the equilibrium and changes of the equilibrium. We show the first equation, the supply side on the top, and the second equation, the demand side on the bottom. In both graphs, the horizontal axes are job tightness, J, which is defined as A over Q, or vacancies per capita. To see why the two functions look like the two curves, we need to use some knowledge of functions. In the first equation, if J increases, the left-hand side of the equation rises. To keep the two sides of the equation balanced, the right-hand side of the equation must rise as well to balance it out. We know that the function PQ is an increasing function of Q, so Q must increase to do that. To summarize, when J rises, Q rises. That is why we have an upward sloping curve to represent the first function. In the second function, if J rises, 1 over J drops. The function m1 over J drops. Again, to keep the two sides of the equation balanced, the right-hand side of the equation must drop. That is why we have a downward sloping curve to represent the second function. As I emphasized many times earlier, graphs are always linked with mathematics. They are just two equivalent ways of looking at the same thing. You cannot do graphs without understanding maths first. Now, if you know all the parameter values, you will be able to determine the equilibrium value of job tightness J from the second equation, or the second graph. Then, use the equilibrium value of J to determine the equilibrium Q by the first equation, or first graph. Once you solve for J and Q, you can substitute them to other equations to solve for other endogenous variables such as unemployment rate U and vacancy rate V, as well as output Y. Note that here I make use of the two properties of the matching function to rewrite the endogenous variables. In particular, if we focus on the solutions of unemployment rate U and vacancy rate V, we can see that when J rises, U drops according to the U equation, while V rises according to the V equation. This implies that U and V are negatively correlated. It is the same as what we observe in the data. This negative relationship is the Beveridge Curve, which is a stylized fact of the extensive margin in the labor market. Now that we obtain the equilibrium of the DMP model, we are ready to apply this model to explaining business cycles in the labor market with the help of comparative statistics. In other words, we try to see the effects of exogenous variables on the endogenous variables. First, let's see the effect of a rise in social benefit, B. This is an unemployment policy made by the government, so we treat B as exogenous. Looking at the two condensed equations, B appears in both. When B rises, minus B drops. The entire term on the right-hand side of the second equation rises. As a result, the equilibrium job tightness J drops from J1 to J2. At the same time, when B rises, the left-hand side of the first equation rises. So at any given level of J on the left-hand side, Q has to rise to balance it out on the right-hand side of the equation. This means that the demand side curve shifts up. At the new equilibrium level of J, the new equilibrium Q drops from Q1 to Q2. In other words, when unemployment benefit B rises, less people are actively searching for jobs. This change is intuitive. If you want more people to participate in the labor market, a government should not set a high social benefit, because a higher unemployment payment will motivate people to stay at home rather than going out to work. Now let's look at the second exogenous variable, productivity Z. Again, it appears in both equations. If Z rises, the right-hand side of the second equation drops because Z is in the denominator. The new equilibrium J rises from J1 to J2. At the same time, if Z rises, the left-hand side of the first equation rises for any given level of J. To balance this, Q must rise for all given levels of J, which means a shift upward of the supply curve. Combined with the new level of J2, the new equilibrium Q rises from Q1 to Q2. This shift is a reinforced effect from both demand side and supply side. The intuition is that a higher productivity motivates a higher participation, which matches the procyclicality of the extensive margin observed in the data. Finally, let's look at the effect of a drop in matching efficiency, which is a key exogenous variable in the DMP model. As E drops, the right-hand side of the second equation, which is the vertical axis variable, does not change. So J must drop to balance this change to maintain the equation. This means that a drop in E shifts down the demand curve, and a drop in drop tightness from J1 to J2. At the same time, a drop in E makes the left-hand side of the first equation decrease. So for all values of J, Q must decrease to maintain the balance. This is a shift downward of the supply curve. The combined effect makes the labor force to drop from Q1 to Q2. The intuition is that a lower matching efficiency dismotives participation. To summarize, a change in an exogenous variable will always shift one or two of the equations. We always start with the effect on the equilibrium J based on the second equation, the demand curve, and then determine the effect on Q based on the first equation, or the supply curve. Today we have seen the static version of the DMP model, which relaxes the classical assumptions of symmetric information and perfect competition. After substituting in the search and matching assumption and the Nash equilibrium assumption, the two condensed equilibrium conditions describe the supply side and demand side of the labor market respectively. The DMP model can explain business cycles in the labor market better, especially the stylized facts on the extensive margin, which cannot be explained by the new classical RBC model. The Beveridge curve is a negative relationship between vacancy rate and unemployment rate, which can also be matched by the DMP model. If you have difficulty in understanding the relationship between maths and graphs, please review the short course on quants. The relevant chapter in this textbook is chapter 6. Have fun!